Hey guys, TJ Schwartz here from Schwartz Knives. I get a lot of questions about fixtures. We make knives in this shop on various CNC equipment and hand equipment, and we have quite a few fixtures involved in doing it. And we've kind of reiterated a lot of these fixtures over the years, and they've culminated in our newest model, which is the Overland X. And I want to show you today every single fixture required to make this new knife. So before we go to the fixtures themselves, I want to show you the platform we're using for our fixtures, which is a Pearson MPS, mini pallet system. Huge fan of Pearson. We love Pearson in the shop. We are converting all fixtures to Pearson. We don't have all of them converted yet, but since running this system, it's taken over the shop. You can see Pearson Workholding here. This is a pneumatic fixture block that is mounted into the machine and has a spring-loaded ball detent system in the middle. Now, it's got hardened pads here that are surface ground and locating pins, and when these balls engage in the bottom of our fixture pallet, it draws the fixture down onto these locating pins and onto these locating pads. And when you apply air pressure to the fixture, it will release the spring pressure on these balls and allow you to take the pallet off. So I will show you that in a machine. As you can see in our X7, we have one base. We have one base in each machine. You have an airline coming in, routed from up here. I do have another video on the install of this, but this is just sort of a quick overview before we go into the fixtures themselves in case you missed that. There's an airline coming in that you can press a button which activates or deactivates the detent ball system to draw the pallets down. And without further ado, let's look at the pallets. Okay, here we go. All of the pallets we use to make an Overland X. I want to show you each and every one, how they work, what we like about them, what we don't like about them, and maybe you can learn something, because I found videos like this super helpful for us. And thank you all out there who have inspired a lot of ideas that have gone into these pallets and fixtures. It's been an awesome industry to be a part of, and I would love to pass that energy along. So this first fixture here is our Tang fixture. That is the entire knife without a bevel, just perimeter machining, precision holes, chamfers, things like that. This is pre-heat treat. So a knife blank will come to us that has been water jet and surface ground. Water jet oversize, about 25 thousandths of an inch all the way around, and surface ground to the precise exact finished knife dimension. Now this first operation is to put precision holes in the blank. The blanks come in without holes. And we do that because water jet holes waste a lot of water jet time, and you still have to clean them up anyway. And anytime you pierce with a water jet, you're wasting time because the water jet has to stay stationary for quite some time to just pierce, and then it can start to move. So when you design fixtures, it's a good idea to have a minimum amount of holes on the water jet side if you can. And so we take that initial piece, that rough blank, we drop it into this section. Now, the way this is designed is we have a clamp up here which holds the blade down. And then we have two tapered countersunk head style screws here that hold the blade down and over. So they basically effectively wedge the blade against this little wall right here. So the blade goes in. Obviously all these bolts and things will have been removed to load the fixture. Blade goes in, it gets wedged over and down, and then the blade gets clamped down. Then the machine comes in, drills, and interpolates the precision holes. You can ream or interpolate, but we interpolate most times. And then over here, it machines the edge of the blade. So the portion of the perimeter that will eventually be the edge is machined to finish. And there's a good reason for that, and I will show you why. So after this op one, we have a water jet perimeter, a machined edge only, and 3 precision holes. That is the lanyard hole and our 2 bolt holes in the handle. So we go to op 2. Op 2 is where we can now bolt through these precision holes and locate with a pin in the lanyard hole. The lanyard hole becomes a critical part of this fixture for locating. So if you can imagine this blade going here, lanyard hole locates on this pin, and then our newly precision machined edge is now touching this pin up here. So in a lot of fixturing setups, you want to have some sort of clocking stop, which is this pin up top, and then some sort of rotating location, because you don't want to over constrain a part or under constrain a part. And the really ideal constraint is something that it can rotate on and something it can rotate against that will contain the knife in all dimensions. There was a time where we used shoulder bolts here that would precision fit through the bolt holes and try to hold it. That is unreliable, because the further these pins are from each other, the more accurate you're going to be. If there's a small tolerancing difference between hole diameters or this machined edge, it's minimized as much as possible the further the pins are apart. So that's what we have here. So it goes up against here. This clamp holds the part down on the blade side, because once again, you have no holes to bolt down. We don't do tabs or bolt hold tabs or anything like that. We have our 2 bolts through the main holes and a clamp that holds it down. Now you'll see on both op 2 and 3, we have a clamp over the edge of the knife. It demonstrates why we're machining the edge in op 1, not just so we can have precision by pushing against this pin, but also because it allows us to do this clamp and fully reveal the perimeter of the knife. Now, anytime you do a partial machining job and then a second op that finishes it, you're going to have a seam no matter what. So the critical thing in designing a fixture is deciding where that seam is. We want the seam to be at corners, which is where the edge begins and ends. So if this is pre-machined and we machine the perimeter, you will never see that transition, because that transition exists in the design inherently. So this is clamped down. The perimeter is machined. We have a weight relief pocket that's machined out. We have a chamfer tool that goes around and chamfers the perimeter. Now, then it flips 180 degrees, and we do the same thing on the other side, except now all that's required is a chamfer. And that's simply because we have the perimeter fully machined on this side. So again, these locations of these pins and the way this is designed is critical for, most importantly, making sure your chamfers match left to right. Because anytime you flip a part, your tolerancing and the way you hold it matters a whole lot. If you can avoid flipping, you can really avoid a lot of the sort of requirements that we have here, but we like chamfers on both sides of our knives, and this is what we have to do. Now, this is a mirror image fixture. We do the same thing coming from right to left and left to right. So this is a 3-op situation. Older fixtures we had were 4-op until we sort of advanced to the point where we realized we could machine the edge, then put it here, cover that edge, and machine. So we don't have to have this stage completed and then subsequently also machine the edge. It's all done here. So this fixture I'm very happy with. There's not a lot I don't like about it as far as how it functions. The one thing I will say is this is a lot of bolts. So the inherent aspect of running this fixture in the real world is you're kind of like a NASCAR pit crew. To unload and reload and advance these blades to the next stages is quite a bit of time of literally just taking screws out. And it's until we get into something more complicated or I come up with a better idea, we're sort of stuck with that. But as far as reliability, it's basically 100% reliable. We don't really have issues with this fixture, which is a win. You'll notice this green thing here. That's something people may ask about in the comments, so I'll mention it. I kind of experimented because we use these clamps, and I wanted to see what would happen if I put a clamp inside of a 3D print. So I paused a 3D print, put the metal clamp inside, and 3D printed around it. I don't know that it really made a difference, so it is that way. It was an experiment. I don't know that it's important. We haven't had a lot of issue with scratching, and furthermore, we make sure that these clamps clamp where the bevel is going to come in and grind away anyway. So you can see the shape of them may look kind of strange, but that's to keep the clamping pressure inside of what eventually will be the bevel, which will disappear. Okay, so blades leave this. They go to heat treat. They're hardened. They come back, and we are ready for bevel grinding. So we have gone away from milling bevels, and we are now bevel grinding all of our bevels. We use a grinding cup wheel, and it requires a very unique fixture. This occurs in a 3-axis mill. You can see this fixture is not only angled this way, but also these pads where the blades sit are angled this way as well. So these are a compound angle. We actually had a shop with a 5-axis machine go ahead and machine these pallets for us. There are other ways to do it, but we found this to be the most efficient and effective for us. So the blade comes in, it's been heat treated. For clarity, this is what it looks like coming off the last fixture. You can see the chamfers, you can see the holes, you can see the pocket, the lanyard hole. This is what it would look like after this fixture. Heat treated, comes in. We have another locating pin in the same manner that we did on the last. We have pins that are far apart, once again, as far as you can get them. So this pin is as far towards the tip as we can allow. And it rotates, you saw it rotate right up against that pin. We have a magnet at the tip, which helps with hold down. And the grinding wheel comes in, one more bolt right here that'll hold this down. The grinding wheel comes in, and it's a vertical mill. So the grinding wheel is not doing anything weird, it's just coming in straight down. And the heel of the grinding wheel right here grinds its way down. And what you get from that is something like this. And then you flip it over. And on this side, you have a little bit of a different constraint, which is that on this side, the wheel puts a lot of down pressure. Usually in milling and end mill or whatever, will lift apart, and everything you're trying to do, like on this fixture, is about holding down. In this, the wheel is pushing down pretty much at all times. And so you don't have to put a lot of effort into hold down. What you have to actually do is prevent things from getting pushed down beyond where you'd like. And where that applies here is, once you have a bevel on one side of the knife and you move to op 2, if you don't have something underneath it and you're trying to run relatively efficient feeds and speeds with that wheel, the blade will push because you obviously have that undercut and air underneath, and you will deflect the blade and you will get inconsistent edge thickness from the back to the front, because as it pushes and pushes, the further forward it gets, the further the blade can be pushed down, and it does very strange things if you don't have support. So what we have is actually JB weld. It's the putty style, and we found it actually to be really reliable for doing this. You could 3D machine and insert, but it's never exact and requires a lot of messing around. So all we do is grind op 1, flip it to op 2 with some putty underneath it, let it harden there, and also have a magnet. So it's being held down by the magnet, it's being held up by the putty, and that will alleviate movement that you may see when grinding. So an interesting thing is also, if it's able to be pushed down in some way, if this wasn't here, when the wheel leaves the tip of the part, if the blade has been sprung down, it wants to spring back up the moment the wheel leaves it, and it'll start doing that at the last, just a little 20 thou of the tip, and you'll actually kind of grind and clip the tip. We call it tip clipping. So supporting it prevents it from going down and then springing up at the end. And the magnet on this side is because the blade, if there's a tiny bit, we're talking a couple thou of lack of straightness on the blade, like let's say this tip wants to come up just with the natural slight bend of any material issues, you could have that same issue where it's pushing not the part down, because it's supported by the fixture, but it's removing any bow the material might have. If it's bowed up, it's pushing it down, holding it flat, and then when it gets to the tip, that spring wants to come a little bit back into the knife as the pressure's relieved, and you can get some weird little deformation at your very tip. So magnets holding down, supports holding up, pins at furthest distances with appropriate angles. And I know this is like crazy. There's a lot more going on here with this cup wheel grinding than what you see, but I'm describing the fixture in this video. Maybe we can talk more about bevel grinding in another video. Okay, up next, we have talked about the Tang machining prior to heat treat, the bevel grinding post heat treat, and that effectively gives you a knife that could be finished. It could be Cerakoted with handwork and with tidying up of any scratches. It could be stone washed. And so that kind of brings us to this point. The only exception is a laser engraving. We do have a laser. It's not, I guess, that interesting, but we do locate this on a laser, engrave deeply that logo, and that's where the knife would be prepared for the following stages, which means we are on to other parts of the knife, which is the scales here. So this is another Pearson pallet. I'm going to turn it a little bit. So it would sit on the machine like this. We have Mighty Bite clamps. These are, I believe, pit bulls, they call them. These are actually planer blades. So we found a company that has a planer that has a blade something like this, and we found that because it's sharp, and we do dull it a bit so you don't cut yourself, because we can have these sharp planer blades that from the store already have some slotting. We can have a little bit of variation in our coupons, and the pit bull will hold it into the fixture, and if there's too much variation for the pit bull to handle, we can slide these clamps to adjust for either poor saw cutting or just overall material that's a little bit unique. So you can see this one's not quite dropping in, so I would have to space this back a little bit. But this is a 5-inch gap, and as long as we can fit a knife inside of 5 inches, we're having some good luck, because a lot of material that you order is 5 inches. Usually 5 by 1.5 is kind of your standard coupon if you're going to buy smaller quantity materials. Now obviously if you're doing huge volume of any one color, we could order it and cut it however we want. But if you followed our brand, we do a lot of unique stuff, and sticking with that 5-inch width gives us a lot of ability to just buy small quantities for unique drops and whatnot. So the coupon is pressed down in, it's clamped over with this Allen wrench, which would push this against between basically two knife edges, because your pit bull has like sort of a sharp edge, and you have a sharp edge here, and you get a jaw clamping. Now the beauty of this fixture is we can either run individual coupons, or we can actually throw a whole 5-inch wide chunk that is this entire width. It doesn't just have to be 1.5 inches. And we do have outlines below, and the purpose for that is if you have coupons that are a little bit variable in width or whatnot, you can make sure that you're not going to miss the overall periphery, the part fitting in the coupon for some reason. So in Op 1, we basically do precision holes and precision chamfers. So this will come off of Op 1 with holes, and those holes counterbored and chamfered. There will be no other machining. And then we can take that, put it onto Op 2, which is merely a little risen plateau with threaded basically standoffs that stick up. So those standoffs allow for the location, and then we screw and bolt down through the counterboard holes so that all 3D machining can be done. And then we end up with all manner of different materials that have been machined. So you can see this is something like what it would look like. So it's able, in this side, once these counterbores and chamfers have already been done, you can bolt it down and the tool does not have to enter those areas and strike those screws. You can do perimeter machining, you can do texture, patterning, chamfers, the like. So that is the scale fixture. This is a culmination of quite a bit of study. The scale fixtures often kind of kick our butt. This material, one of the problems is materials are so variable. Their thicknesses change, widths change, the way they machine changes. We've tried different ways of holding. We've tried expansion pins, which kind of grip from the inside. We've just found that the most reliable way is just to bolt it straight down and to just squeeze along a 5-inch section, because 5 inches is nominal enough that pretty much all material we can get to work. So that is the scale fixture. So now we are on to the sheath fixture. This is a vacuum molding fixture. I'm not going to talk too much about sheath design. I think that'd be a great separate video. We've really advanced. We've done other sheath videos, but we've really advanced in our sheath design ideas. And so I'm just going to talk about the fixture. Like I said, this is a video about fixtures. So this is HDPE. This is basically cutting board material, and you can get it in bulk, readily available, super affordable, lots of different thicknesses. Cutting boards are ubiquitous. So we source the HDPE, and then I would point out we have this thing laminated to a piece of aluminum. You can see there about a 1/2-inch piece of aluminum. And the reason for that is we've done vacuum molding fixtures. This is thermoforming, so we're heating Kydex and we're vacuum molding it over this. If we just do HDPE, which we've done in the past, it has a tendency to get warm and sort of distort. It can warp and flex a lot. And so the aluminum is stiff enough to hold it flat. And we've also tried just making the whole thing out of aluminum, and that is problematic because aluminum cools things down really fast, which you would think would be good. Okay, put it on there, it'll cool down fast. But it cools it down so fast that it will actually warp the Kydex because you're cooling the bottom of the Kydex faster than the top, and it likes to potato chip and bow. And so the only way to get the aluminum to fixture to work that we've run is we have to preheat it, because if it's at room temperature, it cools too rapidly. Whereas this is a combination of the best of both worlds. The HDPE does not overly cool the Kydex, and the aluminum keeps it stiff and offers sort of a heat sink, which keeps the HDPE cooler, and it works really good. This is pretty much the standard I plan to use moving forward. I don't see a reason not to do this laminated setup. So we have a 3D machined sort of boss. We have 3D machined blade section. We have separate independent scale pieces. This is just because scales are where most of your engagement with the knife occurs and where your retention occurs. And it's better, I've found, to have these independent and separate so that you can tune and adjust. We went through probably 7 or 8 different scales to get the retention correct. And once you have this with the right amount of clearance, it doesn't really affect retention that much. So you can get something that is ready to go and then fine tune on the scales alone instead of just remachining an entire piece of HDPE half a dozen times to try to get this retention right. So it's a vacuum fixture. So you can see, maybe you can see there's tiny little holes all along some of these points where you might need the Kydex to really suck in around this. And so the way that the vacuum works is we drill tiny little holes all around the perimeter in places that it requires that suction. They go all the way through the HDPE, and then in the bottom of the HDPE we machine what looks like a snail trail. If you ever pulled bark off a log and you see like where the bugs have eaten little channels, there's a channel in the bottom of the HDPE that connects the dots. Basically, it's like a constellation. So all these holes going through are getting connected together under there. And then there's a section of that channel where it comes over here where we have a push to connect fitting. So a vacuum line can send vacuum through that whole channel and to all these little holes. And then, of course, the aluminum on the bottom seals that. So we put, a bead of RTV around the perimeter, seal it, so that when you charge this thing with a vacuum, it's a distribution manifold of vacuum to all these little holes. I love this setup. It doesn't require a dedicated vacuum table. It's reliable. You don't get vacuum leaks, and it's really pretty easy to make. So you would heat the Kydex in actually a t-shirt press, put the Kydex on top, take this, press it on top. You can see it fits around that boss. Hold it down. We have a foot pedal that activates the vacuum, sucks the Kydex down. Once it's cooled a little bit, take this off. You now have a piece of Kydex that has a skirt. Now the skirt is extremely important in this case because we're going on to the next fixture. This is another Pearson pallet. This is for machining the actual sheath fixture. So you can see we've got a few features here. We've got some magnets in here. We've got a matching boss. So we've got this rectangle. We got a matching one here. And so when you come off of here, where this is sealed, that skirt around the perimeter, it's formed a very definitive rectangle. And then that can take that imprint in the Kydex and slide over that same boss on this fixture. Now you can use more of like locating pins that the Kydex wraps around, but there is a problem with that, which is if you have, let's say, 2 pins for locating, it's going to stretch the Kydex across the axis, or maybe even compress the Kydex across the axis where the pins are. With a rectangle, it's going to basically kind of spread that Kydex and lock onto this with sort of equal force in all directions. It just keeps the distortion low because Kydex moves, it shrinks, it grows. Different colors of Kydex do different things. So this is a really good way to keep your precision. So we slide it on here. We have this piece, which is magnetic. You can see magnets in it. Sticks on there, holds the flange because again, you have a skirt. This is holding it down. We can then come in and machine stuff. Now, sheath design, sheath execution, and how we're doing a lot of this other stuff I think is better fit in another broader video about sheaths that shows sort of where we're at. And I just wanted to talk about the fixtures. Again, a Pearson pallet here and a vacuum mold here. So I know this is kind of a speed run through these fixtures. Not a ton of detail. I bet there's gonna be a lot of questions. I wanted to inspire some questions because I do want to make more videos about our processes. I love sharing this stuff. If you see anything here that makes you scratch your head or you want to see a dedicated video about, let me know. I know people are going to be asking about the bevel grinding. That would be a cool thing. And yeah, I appreciate you guys following us, ordering knives from us, stopping by to see kind of how we do things. Maybe you're a knife maker and this can help you. Maybe you just like to see how things are made and you watch that show on Discovery Channel like I did as a kid. Regardless, thank you guys for stopping by, and till next time.